Floor is yours.
Can you hear me okay? Because I mean, oh, okay. Yeah, I think you can now. I kind of lost my voice. So thanks. Okay, actually, who doesn't know how instrumented PGO works whatsoever? Like, I just want to have an idea how.
Does not or does?
Well, how it works. Well, very good. Okay, so people are familiar with PGO and instrumented PGO. And who wasn't here earlier at Wen Lei's presentation from Meta about CSS PGO? You weren't. Okay, some people weren't. Okay, so okay, that helps me. Thanks. So not much to spend here because I don't, we just did that, right? So we have instrumented PGO. One thing to note is that a lot in the way instrumented PGO works is that he kind of assumes that you start the program, something interesting happens, right, and then the program ends, and then you get your profile. And that's not really how servers, for example, work, right? So servers are about, you start the program spends a bit of time to set up what actually matters, which is a bunch of like queues and worker threads and then the interesting thing happens, right? Like then actually those worker threads start handling requests. And the thing that we care about is those, whatever happens to handle those requests, not so much what happened after main started. And in fact, main never ends. Like there's no meaningful end of a server. They might get preempted or whatever, so we don't care about them ending. So we even the way we collect profiles on the server side is with an RPC. Like we go and say, hey, okay, now that you started, how about you reset everything that you've seen so far because it really doesn't matter. And then we wait a bit and then we collect the data. So to whoever wasn't, so Wen Lei explained this way better. The problem with profiles in general, right? Like it doesn't matter if they're collected with instrumentation or via sampling, is that the way we collect them today is that you get per function a kind of like an aggregate of whatever happened to that function in all the scenarios in which it might have been called, right? So when you start doing inlining and you use the profile, you start diluting the quality of the caller too, because you basically say, oh, well, I have no idea what, like what these functions really used to, like in this particular context. So I just go and copy what I'm being given. And now the caller is tainted, and then everybody up from there is tainted too. So you end up with like a worse profile, right? So worse profile, worse performance improvements, and it sucks. And actually the reason I started doing this, because normally I work on ML guided optimizations, is because I needed like higher quality profiles, and I was trying to measure what it says there, like, can I estimate the number of instructions for an RPC, which you think you should be able to do, like, you have profiles and you go in the, like at assembly print time and you look at the assembly that you produce, you think, with a bit of smart code, you should be able to do that, and I wasn't. And the reason was this loss of contextualization. So contextual profiles do that. Now, a question, of course, is like in the context of what, right? Because it's of the caller and the caller's caller and the caller's caller's caller, right? So this path starts somewhere, right? And I mean, that kind of matters, right? The challenge for instrumentation in particular is that if you want to do contextual profiles, that the mindset has been like, oh, but the number of counters we have to pre-allocate is going to explode and like misery is going to happen. And that doesn't have to happen, actually, because coming back to the thing of like, what do servers do, right? So all we really care about is what those tasks that they get executed, the request handling that happens, that's what it really matters. But for some reason, that's what really matters, but we don't tell the compiler what that is. Like, we just say, hey, here's a bunch of code you can compile, and by the way, there's main that we all know about, but the stuff that actually matters to optimize the words, right? Like, retiring RPCs quickly, it's hushed, right? Like we don't say that they're there. So it's like, well, what if we actually tell the compiler, like, here's the list of functions that matter, right? And that's what we actually even forget about profiling. That's what actually you should strive towards optimizing, right? Like the call graph under this function should get faster, right? And let's see, I mean, well, that ended up being like very useful for collecting profiles too, instrumented profiles. Like it completely simplified the problem that I mentioned earlier. I'll explain how. But of course, you're going to be like, well, how do we know what these things are? Well, like, let me put it this way. It's not that they appeared out of like, like thin air, and like as a binary author, you're surprised that your binary is executing RPC requests, right? So you put them there, or whoever you are, like the system architect or whatever. But in extreme, they could also be detected dynamically, because it's dynamically for a very static property of the binary, right? Like you could through sampling just see where is this binary spending time, right? And do it that way, right? If you really, really want to not know what they are, right? But you do. So let's get to what I ended up doing for instrumented contextual-based profiles. So I'm passing that information to the compiler, right? I'm giving it a list of, hey, here's the entry points that you should actually care about. And then the instrumentation, like the way PGO works today is that there's like a phase in which we introduce those intrinsics, and then we lower the intrinsics to counter increments, right? Most of the first part stays exactly the same, like not almost, no, exactly the same, right? So all the logic about like finding the minimum span tree, all of that is all the same because it doesn't need to change. We introduce a new intrinsic. You can read what it is, and it's not surprising what it is. And then the lowering is different, right? So instead of having global arrays, like for each function has its global, bag in which we counter increment, we get those things from the runtime, so from compiler RT. So basically every function goes and says, hey, give me the context that I need. And then we have to lower that call site somehow, and I'll show you actually with an example how that looks like. Hold on. All right. So first, the context itself, so the data that where the counters are, is just a contiguous chunk of memory with a small header. The only important thing in that header is that it identifies the function, and you can also link these things in a linked list. You'll see why in a second. And then the counters are somewhere, and then the call site. So basically, like for each call site, we're going to want to link the context of the callee in that array there, right? So then we form a tree of contexts. Okay, so if these are two functions, one is called an entry point, which is an entry point, and then another one is called a callee, which the first one calls. The blue stuff is like stuff that we do today. So it's literally the intrinsics that we have today. The red stuff is the new one, right? You'll notice that the new one captures the called value, because I chose to show an indirect call, because it kind of then covers everything. But that's about it. And they're also indexed, right? Because there's an array in which we'll have to insert them. Lowering time, so this is IR-ish, because I didn't want to show gaps and loads and stores, and everybody will spend time reading those and figuring out actually what I'm showing. So the only important things is that the entry basic block counter increment is lowered to either start context, to the LLVM instaprof start context, and that's for the entry point. Everybody else does get context, okay? The actual counter increments are literally counter increments into a local variable. That's all. Like, before it used to be global, now it's local. That's the only difference. For the call site, we save on thread local storage. So there's a well-known, like to both compiler RT and to the compiler, there's a well-known variable, like thread local variable. Actually there's two, but fine. We save the expected callee. So we say, hey, like we're about to call this function, and you're going to be, why do you need to do that? And you'll see why in a second. More importantly, we save the place into that call sites array, into the local context in which I expect the callee's context to be linked in, right? And then I make the call. So I make the call, and we happen to get, in this case, to a callee. That thing goes and calls promptly get context, then get context says, okay, so skip the pink side, I'll explain that in a second. It goes and say, okay, well, has this happened before, right? Like, have we been in this situation before, and therefore I should find linked to the call site info there, like context for me? So the answer is no, because this is the first time, and then we'll bump allocate that. We have an arena that I haven't mentioned yet, but now I am, and we bump allocate that there, and we link it in, right? Well, the second time this happens, we're going to find it there, right? In the case of direct calls, this is all there is, right? Because in the case of a direct call, you're never going to discover another callee haven't happened there, right? In the case of an indirect call, we just maintain a linked list, which means that every time in the case of an indirect call happens, you're going to do a linear traversal. Oh my God, how bad that can be. It's not really, because really in reality, the fan out at the indirect call site is not that bad. And I have data to show that. Just want to stress the fact that the context produced for a function depends on its position in the path from the entry point. In this case, foo is called the two different positions. They should have come clear from the way it's being constructed. But, I just wanted to stress that out. Entry points are special, of course. That's why we have a special function for them. So the compiler will produce for each entry point a object like that, like a global object. So we do have global objects after all. On which we latch the arenas on which we bump allocate all the stuff. Importantly, there's a lock there. So the key thing is that, this is server side. So a lot of threads are trying to execute the RPC request, right? Only one acquires at a time the lock for the particular RPC that we, are profiling. So the other ones are not going to sit and wait, right? They're going to get something back. And what they get is a scratch context. So the scratch context is what it kind of suggests it is. It's a chunk of memory that you can write into and nobody cares what you write in there. The main thing is that the counter updates are not seg-faulting, so that's great. The other great thing is that it's understood by the compiler runtime. So every time the get context is called and he sees that the pointer being given to latch its context into is an interior pointer into one of these things, it promptly returns a scratch context, right? So it's basically once you go to the scratch context land, it's over, right? Like you're not collecting profiles anymore. Okay, so what's up with all of that? We save the call site, and why are we doing that? And well, because signal handlers happen actually on server side quite a lot, right? So, which means that you execute your thread and suddenly a function pops into existence and says, hey, give me a context, right? So what can happen? Well, what we want it to do is not start messing our profile, and it will realize very quickly that either nobody asked it to be there, meaning like there's no, nothing in the thread local storage that says, here's where you need to link yourself into, or that nobody expected it to appear, right? And then it returns scratch context, which means that also whatever it calls, because the signal handler is not necessarily trivial, it might call its own other things, also lives in the scratch context, meaning it doesn't pollute the context that we care about. We do nothing special about recursion. If it's not Stack Overflowing your program, it should be fine on the heap, right? We do nothing about tail calls, although we might need to, but we don't right now. And with what I'll show you, I didn't do anything special. Tail calls could be smartly, handled because we know that they happen, right? Like it's not like, I don't know, is there a tail call? Well, we know that, when it starts, and we could model it more like a loop of context, but we don't do anything special right now. And then finally for the profile, so when the RPC comes and says, hey, save the profile, we just dump the arenas to disk with a bit of a header to be able to disambiguate the pointers. And then we come with a processing tool. The only reason we're doing this, by the way, is because taking a dependency on anything from compiler RT is not something you want to do. And that's why, literally, right? So we use bitstream because it's a nice nested, it's basically JSON but binary, right? So, and it's already in LLVM, and it's great. So it was the obvious choice. Okay, so I took the search binary. I work at Google, but other people have search binaries too. But anyway, I took the search binary and I did all this to it, right? So it has two workloads, which we'll call large and small. They're called something else. And at runtime, the overhead was actually kind of small. So it turns out that the actual overhead of the profiles, the trees themselves was not that big. And that's kind of expected because after you discover all the interesting paths, you're just going to keep reiterating over the same tree over and over. It effectively compresses at infinite, right? The only dynamic overhead that is not really dynamic, as we don't allocate threads like maniacs. We allocate a set of threads and then we kind of keep that, was the scratch context, which I pessimistically set it to 1 meg because I didn't want to see what it actually should have been. And I ended up with about a gig or so extra runtime overhead, which doesn't really matter. The profile is small. So how come it's so small? Because you're saving a lot of stuff. Yeah, but the profile of the other guy, like the normal FDO, is large because it saves a lot of code. Like it saves everything, code or not, right? And it turns out on server side, most of the stuff is code. Well, there's a startup, but nobody cares about that. At runtime, most of the code, like 90%, is kind of cold. So, okay. Lots of profiles, lots of contexts were collected with lots of counters. Most of counters are 0. That's not very surprising. The trees are non-trivial. Like, you can see the numbers. The binary size, well, we kind of win, but we kind of cheat, right? Because the text size increases, no surprise. We have to, we do function calls for Christ's sake, and we have to handle those call sites. It can be probably, that right side number can be pushed slightly to the left, but not by much, I don't think. We don't have the global objects for the counters, right? So that's how we cheat. It's what it is, okay? And it's faster than the normal IFDO. So you're going to be, okay, this guy's lying, right? But since I don't do animation, you can read the bottom. So what happens is the normal IFDO does a lot of shared writes. Like again, it comes from an error of like, surely your program has only one thread, and you start, you do something and you end, right? Well, these don't do that. So there's a lot of like performance overhead happening actually on server because of shared writes. And actually, my colleague has a patch for the normal IFDO is trying to like mitigate some of that. Well, this approach completely bypasses all of that because I'm only collecting on a single thread, right? Like everything is thread local effectively, right? So long story short, I made a mistake at a point where I didn't make it thread local, like the scratch context, and because everything was like grouping to write at the very beginning, because everything has a few counters, right, and everything would try to write at the very beginning, things were slower 20x than the normal IFDO. Well, there was an easy fix, and now we are like 5 times faster. All the characteristics are basically better. Again, this works for server, and that's what I care about. Right, so when you look at the counters, please note this is a log scale. Really what this says is most contexts are small, right? And separately, most contexts have lots of 0 values, right? This captures that aggregate that I showed earlier, but in a more more fanned out graph. Same for call sites. Most contexts don't fan out too much, right? And when they do, most of the call sites won't actually get exercised, which makes sense because you have a lot of error handling code, and you hope you don't hit those right during normal runtime. Most indirect call sites call very few alternatives, but there is some extremes. There are some extremes. Yeah, go ahead. I don't know because I was too lazy to look, but I wouldn't be surprised. Like, yeah. I mean, look at that, 80, probably. In terms of like context distribution, so most of the context counts are the same, like at the mid-level, which is not very surprising. I thought of like painting the graph, but I don't know if I can read. This seems more detailed than just seeing like a, like a cloud. Okay. What about non-server? Like it's interesting. And actually one of the feedback was like, well, what about non-server? Yeah, what about non-server? So let's see. So I took opt and I made it build the IR of passbuilder.cpp. So I extracted the IR with the tools that we use for MLGo IR collection too. Like it's all public, obviously, but it doesn't matter. So, and I just recompiled it with whatever, right? And it's slow. Of course it's slower, right? Because I mean, like there's no things like shared writes or anything like that. And it's about 2x slower than and 2x is generous because I'm presenting, So it's 2x slower, right? And the profile is bigger than the normal profile. And the one thing that is kind of curious is that the actual runtime memory usage is not incredibly bigger, right? So I mean, server-side tasks take like milliseconds, right? Like tens of milliseconds, whatever. But I mean milliseconds. This thing took like 30 seconds, right? And it worked there hard. And yet the profile size did not blow like by a similar order of magnitude, right? So why? Other than that, like I'm not gonna dig much into this. It's more like the types of distributions are similar. Probably I wasn't surprised by that. So again, call size, same thing. Indirect call target, again, same thing. Like like things don't fan out. Bulkiness in the middle somewhere. Here's an interesting tidbit, which, like again, if you think about server side, is not very surprising. So on server side, you don't process a ton of data in one request. You're doing it wrong if you did, right? You shard your data and you have small loops, right? In opt, you don't have an alternative. You gotta finish what you're given, right? So you end up with like relative to the entry point, very small numbers comparatively server side versus, like classical, like, opt type of programs, which is one of the reasons probably this is happening. Like, well, this is one reason, there's a second reason. So this reason is just saying like, well, there's a lot of paths being re-traversed, so you spend a lot of time, but you're not discovering new trees. The second reason is that on the server side, I had like, I don't know how many hundreds of thousands of different requests, right, that I visited. So I kind of exhausted the profile. Here I only gave it one, so I'm pretty sure that if I compiled more, I would have ended up with a much, much larger profile, right? Yeah. Okay, so plans and speculations. So the idea is to continue this, and for the use side of things, like there's already a patch that I landed last year, which is leveraging the notion of a workload. So this notion of like, hey, you have like a magic entry point under which like something interesting happens. why don't we just get all of that something interesting in one module and like effectively do like a fat thin LTO, right? That landed last year with some small modifications, like it will be used for the use of this. And then for post-link, it's basically like like when Lei was saying, like, I mean, like we want to, the current inliner is not really suitable. Also, like it intermingles with like, what's it called, like function simplification and other things like this that doesn't really work well. The idea is to use the module inliner. So basically do all IPO first and then do other things, which we can relax by bringing more awareness of contextualization to some select passes, whatever those are, right? Like whichever we feel that is worth doing. I saw that. Which is where, like, okay, by the way, like what happened is I lost network connectivity. I saw that I had a typo. I fixed it and then it fixed itself again. Like, sorry. So it's CSPGO, not SSS. I'll fix it in the final. The idea is that probably with more collaboration, we can have like an abstraction that both of, like we can basically reuse whatever work we do for pass awareness of contextualization in both. There's an RFC that I wrote, but I was too lazy to send because I went on holiday. There's a showcase PR that I wasn't lazy to produce, meaning like that's not going to land as is, I'll chunkify it. And I think there is some value in this notion of bringing that notion of taskness, like of the magic entry points to the compiler's awareness for more than just this. That's it. I'm 55 seconds off. Okay, thanks.
Thank you. We have 5 minutes for questions. Yeah.
Hey, thanks for the talk. So it looked like your instrumentation, like on the op case, was, there was some overhead that you probably don't want. I mean, it was way more overhead than you have in the other case. Yeah. So this seems to be
sucks. Yeah.
At the border of problematic.
Yeah, probably.
Do we think that the instrumentation that you put in looks pretty trivial? Like there don't seem to be any smarts involved, because like paths that we can statically determine, why do we need to runtime collect those trees? I mean, if you only have direct calls, we kind of we could.
I agree. So my position here was like, first I wanted to solve something that I deeply care about and get paid for, right? So which is like. Which is server side, right?
Fair enough.
There, it does way better, right? As is. And this is a prototype that took me like a month to hack and another month to actually debug, because I was very smart, yeah. So you're right. There's a lot of, for the normal case, there's a lot that can be done that is smarter than this, right? This just says, honestly, this is what it is, right? With what it is today. So this is not a done deal, right? Like we can improve it.
Okay, cool.
Yeah, cool.
Thanks.
Yeah.
We have time for more questions. Keep them coming.
Okay, I confused everyone. Great. Okay, success. Just run under the radar and cool. Okay, I can unplug. No. Okay.
One. Yeah.
It's okay. Cool. Okay.
Well, let's thank our speaker once again.